In the infinite depths of space, the James Webb Space Telescope has unveiled secrets so profound that they challenge everything we thought we knew about the scale, age, and structure of the cosmos itself. As you settle into this gentle journey tonight, imagine looking through the most powerful eye humanity has ever built. An instrument that has shown us galaxies stretching across nearly 800 cosmic neighbors in just a tiny slice of sky, revealing that our universe is far larger, stranger, and more magnificent than we ever dared imagine. Before we embark on this awe-inspiring voyage through cosmic discovery, please take a moment to subscribe to our channel and ring that notification bell. Your support helps us explore the most profound revelations about our universe with the wonder and scientific rigor they deserve. The James Webb Space Telescope, as it orbits silently at the second Lagrange point, 1.5 million kilometers from Earth, its golden mirror reflecting the light of the most distant galaxies in the universe. This remarkable instrument represents humanity's greatest leap forward in cosmic observation, capable of detecting objects up to 100 times fainter than Hubble, and peering back to just 180 million years after the Big Bang, a time when the first stars were igniting in the primordial darkness. The largest map of the universe, created with data from the James Webb Space Telescope, shows almost 800,000 galaxies crammed into a tiny piece of sky and spanning almost all of time. This extraordinary census represents our most comprehensive view yet of cosmic structure, revealing the intricate web of matter that stretches across billions of light-years and traces the evolution of the universe from its earliest moments to the present day. Consider the technological marvel that makes such observations possible. Webb's 6.5-meter primary mirror, composed of 18 hexagonal segments coated in ultra-pure gold, collects infrared radiation that has traveled across cosmic distances for billions of years. This light carries within it the encoded history of galactic formation, stellar evolution, and the expansion of space-time itself, information that Webb decodes with unprecedented precision and sensitivity. Drift deeper into the profound implications of Webb's observational capabilities. The universe is expanding, and that expansion stretches light traveling through space in a phenomenon known as cosmological redshift. The greater the redshift, the greater the distance the light has traveled. As galaxies recede from us due to cosmic expansion, their light becomes stretched to longer wavelengths, shifting from visible light into the infrared spectrum where Webb's instruments excel. The telescope's position at the L2 Lagrange point provides it with a stable observing platform that remains in constant shadow from the Sun, Earth, and Moon. This location allows Webb's instruments to cool to temperatures approaching absolute zero, reducing thermal noise and enabling the detection of incredibly faint infrared signals from the most distant cosmic objects. The cold, dark environment at L2 creates optimal conditions for observing the heat signatures of ancient galaxies. Picture the moment when Webb's first deep field images were processed and revealed to humanity. Astronomers unveiled the James Webb Space Telescope's largest view yet of the early universe in a richly detailed catalog of nearly 800,000 galaxies. Each point of light in these images represents an entire galaxy containing billions of stars, and the collective view spans almost all of cosmic history. From galaxies we see as they appeared just a few hundred million years after the Big Bang, to others as they exist in the relatively recent cosmic past. The infrared sensitivity that defines Webb's observational strategy opens windows to cosmic phenomena invisible to previous generations of telescopes. Why is a powerful infrared observatory key to seeing the first stars and galaxies that formed in the universe? The answer lies in cosmological redshift. As light from the earliest galaxies travels across the expanding universe for billions of years, it becomes stretched from its original ultraviolet and visible wavelengths into the infrared spectrum that Webb can detect. Consider the profound time dilation effects that govern our observations of distant galaxies. When Webb observes a galaxy with high redshift, it's not just seeing that galaxy as it was long ago. It's observing cosmic conditions that existed when the universe was much younger, denser, and hotter than it is today. These observations provide direct evidence of cosmic evolution, showing us how galaxies, stars, and large-scale structures have changed over billions of years of cosmic time. The telescope's spectroscopic capabilities allow astronomers to analyze the chemical composition of distant galaxies with unprecedented precision. Using Webb's NER-SPEC, near-infrared spectrograph, they obtained a spectrum of a record-breaking galaxy observed only 290 million years after the Big Bang. This corresponds to a redshift of about 14, which is a measure of how much a galaxy's light is stretched by cosmic expansion. Webb's discoveries are revealing unexpected aspects of early cosmic history. The James Webb Space Telescope has done something utterly astounding. It has captured a remote cosmic structure that dates back 13.8 billion years in time, almost to the very edge of the observable universe. These observations show that large-scale structures formed earlier and more rapidly than previous models predicted, forcing astronomers to revise their understanding of cosmic evolution. The contrast between Webb and previous space telescopes highlights the revolutionary nature of its capabilities. While Hubble excelled at visible light observations, Webb's infrared vision penetrates cosmic dust clouds that obscure optical telescopes, revealing star formation regions and galactic cores previously hidden from view. This complementary perspective has transformed our understanding of how galaxies form, evolve, and distribute matter throughout the cosmic web. Picture the data processing challenges involved in analyzing Webb's observations. Each deep field image contains information about hundreds of thousands of galaxies at different distances and epochs, requiring sophisticated algorithms to separate nearby objects from ancient ones and to measure redshifts with the precision necessary for cosmological analysis. The sheer volume of data represents one of astronomy's greatest computational challenges. The telescope's observations are providing crucial tests of cosmological models that describe the universe's evolution. Webb's measurements of galaxy distances and redshifts contribute to studies of cosmic expansion, dark matter distribution, and the formation of large-scale structure. These observations serve as fundamental calibrations for our understanding of cosmic geometry, composition, and ultimate fate. As Webb continues its mission, each new observation adds depth and complexity to our understanding of cosmic scale and structure. The telescope serves as humanity's time machine, allowing us to observe the universe as history written in the light of distant galaxies and providing direct evidence of the processes that shaped the cosmos we inhabit today. But perhaps Webb's most profound contribution lies not in any single discovery, but in how it has fundamentally altered our perception of cosmic scale and the true size of the observable universe. In the gentle precision of astronomical measurement, imagine the sophisticated techniques that Webb employs to determine distances across cosmic scales so vast that traditional methods of measurement become meaningless. Distances where kilometers and miles give way to light years, and light years themselves stretch into billions, creating a cosmic ruler that measures not just space, but time itself. The art of cosmic distance measurement represents one of astronomy's greatest challenges and Webb's most profound contributions. Picture the fundamental relationship between distance and redshift that governs Webb's observations of distant galaxies. As the universe expands, galaxies recede from us at velocities proportional to their distance, a relationship known as Hubble's law. The James Webb and Hubble Space Telescopes have confirmed that the observation is not down to a measurement error, providing crucial validation for our understanding of cosmic expansion while revealing puzzling inconsistencies in the expansion rate measurements. Consider the ladder of cosmic distance measurements that allows astronomers to probe the far reaches of the observable universe. For nearby stars, parallax measurements provide direct geometric distances. For more distant objects, standard candles, stars, and supernovae with known intrinsic brightness serve as cosmic lighthouse beacons whose apparent dimness reveals their distance. Webb extends this ladder to unprecedented distances using sophisticated spectroscopic techniques. Drift deeper into the precision required for measuring distances to the most remote galaxies. Webb's spectrographs analyze the light from distant galaxies to identify spectral lines from specific elements, hydrogen, oxygen, carbon, whose wavelengths have been stretched by cosmic expansion. The amount of redshift in these spectral features provides a direct measure of how much the universe has expanded since the light was emitted, allowing astronomers to calculate both distance and cosmic age. The relationship between redshift and distance becomes increasingly complex at cosmic scales due to the changing expansion rate of the universe over time. They measured the distance to 10 nearby galaxies and measured a new value for the rate at which the universe is expanding at the present time. Their measurement, 70 kilometers per second per megaparsec, overlaps the other major method for the Hubble constant. This Hubble constant measurement represents the current expansion rate, but the universe's expansion has accelerated due to dark energy. Picture the mathematical elegance of converting redshift measurements into cosmic distances. Using Hubble's law, the redshift can be used to estimate the distance of an object from Earth. By combining redshift with angular position data, a redshift survey maps the 3D distribution of matter within a field of the sky. Webb's observations create the most detailed three-dimensional maps of cosmic structure ever achieved, revealing how galaxies cluster and evolve across cosmic time. The concept of look-back time becomes crucial for understanding Webb's distance measurements. When we observe a galaxy with high redshift, we see it as it existed when the universe was much younger. The light from the most distant galaxies detected by Webb left its source when the universe was less than 1 billion years old, traveling for over 13 billion years to reach our telescopes today. Distance and time become inextricably linked at cosmic scales. Consider the challenges of measuring distances to objects at the edge of the observable universe. It can detect objects up to 100 times fainter than Hubble can, and objects much earlier in the history of the universe, back to redshift Z20, about 180 million years cosmic time after the Big Bang. At these extreme distances, galaxies appear as they were during the cosmic dawn, when the first stars were igniting and heavy elements were being created for the first time. The precision of Webb's distance measurements enables detailed studies of cosmic evolution and structure formation. These observations are used to measure detailed statistical properties of galaxy clustering, dark matter distribution, and the rate of structure formation throughout cosmic history. The three-dimensional mapping of galaxy positions reveals the cosmic web, the largest structures in the universe formed by dark matter and ordinary matter clustering under gravitational influence. Picture the collaboration between different measurement techniques that create a comprehensive view of cosmic distances. Webb's infrared observations complement radio surveys, X-ray observations, and optical measurements to create multi-wavelength maps of cosmic structure. Each wavelength reveals different aspects of galaxy properties and evolution, while precise distance measurements tie everything together into a coherent picture of cosmic architecture. The uncertainty principles that govern distance measurements at cosmic scales reflect fundamental limits of observational astronomy. Photometric redshift measurements, which estimate redshift from broadband color measurements, provide approximate distances for millions of galaxies but with limited precision. Spectroscopic measurements, which analyze detailed spectral features, provide much more accurate distances, but for smaller samples of objects due to the time required for detailed observations. Consider the statistical analysis required to extract meaningful cosmological parameters from Webb's distance measurements. The distribution of galaxies at different distances and redshifts provides information about cosmic geometry, the density of matter and dark energy, and the rate of cosmic expansion throughout the universe's history. These measurements serve as fundamental tests of cosmological models and help constrain theories about the universe's ultimate fate. The systematic errors that can affect cosmic distance measurements require careful calibration and cross-checking. Dust extinction within distant galaxies can dim their observed brightness and bias distance estimates. Gravitational lensing by intervening mass concentrations can magnify or distort the apparent brightness and positions of background galaxies. Webb's multi-wavelength observations help astronomers identify and correct for these systematic effects. Picture the future improvements in cosmic distance measurements as Webb continues its mission and new telescopes come online. Ground-based surveys will measure redshifts for billions of galaxies, while space-based telescopes provide detailed follow-up observations of the most interesting objects. The combination of large surveys and detailed observations will create increasingly precise maps of cosmic structure and evolution. The philosophical implications of cosmic distance measurements extend beyond technical astronomy to fundamental questions about the nature of space and time. Our ability to measure distances to objects billions of light-years away demonstrates the universality of physical law and the interconnectedness of cosmic structure. These measurements reveal that we live in a universe with a definite age, size, and evolutionary history, parameters that can be measured with scientific precision. As Webb continues to refine our measurements of cosmic distances, it provides increasingly detailed answers to fundamental questions about the scale and structure of the universe. These precise distance measurements form the foundation for understanding cosmic evolution, the distribution of matter and energy, and humanity's place within the vast cosmic architecture that surrounds us. But beyond mere measurement lies a more profound revelation about the true scope of cosmic reality. In the profound depths of cosmic contemplation, imagine standing at the ultimate frontier of human knowledge, the boundary of the observable universe, where the light of the most distant galaxies marks not just the limit of our vision, but the edge of causally connected reality itself. This cosmic horizon, illuminated by Webb's unprecedented observations, represents a boundary beyond which no information, no light, no influence from distant regions can reach us, creating a spherical shell of observable space that contains all of cosmic history accessible to human investigation. Picture the mathematical elegance that defines this cosmic boundary. We can estimate that the observable universe is about 92 billion light-years across. This enormous distance, far greater than the 13.8 billion years that light has been traveling since the Big Bang, reflects the expansion of space itself during the journey of ancient photons. The universe has been stretching during the entire time that light from the most distant galaxies has been traveling toward us, creating a cosmic horizon that extends far beyond what simple geometry would suggest. Consider the profound physics that govern the boundary of observable space. The observable universe is not limited by the age of the universe alone, but by the interplay between cosmic expansion and light travel time. Can the James Webb Space Telescope see galaxies over the universe's horizon? The answer reveals the subtle relationship between causality, information, and cosmic geometry that defines the ultimate limits of astronomical observation. Drift deeper into the concept of cosmic horizons and their relationship to cosmic expansion. During the early moments after the Big Bang, space itself expanded faster than the speed of light, a period known as cosmic inflation. This inflationary epoch saw the volume of the cosmos increase by a factor of 10 to the power 26, equivalent to a fingernail suddenly growing 10.6 light-years long. This exponential expansion created regions of space that remain causally disconnected from our observable region, lying forever beyond our cosmic horizon. The particle horizon represents the maximum distance from which light could have traveled to reach us since the Big Bang. But the universe's expansion complicates this simple picture. Light from the most distant galaxies was emitted when they were much closer to us than they are today. During the billions of years that this light has been traveling, cosmic expansion has carried these galaxies to much greater distances. Distances that now exceed what we can observe directly. Picture the moment of last scattering, approximately 380,000 years after the Big Bang, when the universe became transparent to light for the first time. The cosmic microwave background radiation that Webb and other telescopes observe represents the afterglow of this moment, marking the surface of last scattering that forms the ultimate boundary of electromagnetic observation. Beyond this surface lies the dark age of cosmic evolution, accessible only through gravitational wave observations and indirect inference. The concept of the cosmological event horizon adds another layer to our understanding of cosmic boundaries. While the particle horizon marks the boundary of what we can observe from the past, the event horizon represents the boundary of what we could potentially influence in the future. Galaxies beyond this horizon are receding so rapidly due to cosmic expansion that light signals we send today will never reach them, creating a fundamental limit to communication and causal influence across cosmic scales. Consider the relationship between Webb's observations and these fundamental cosmic boundaries. Using the unique infrared sensitivity of NASA's James Webb Space Telescope, researchers can examine ancient galaxies to probe secrets of the early universe. The telescope's ability to observe galaxies at redshift Z20 approaches the practical limits of electromagnetic observation, revealing cosmic conditions when the universe was just 180 million years old and the first stars were beginning to shine. The three-dimensional structure of the observable universe creates a cosmic hierarchy of distance and time. Nearby galaxies appear as they were millions of years ago, intermediate galaxies as they existed billions of years ago, and the most distant galaxies as they appeared when the universe was in its infancy. This creates a natural cosmic time machine where distance equals look-back time, allowing astronomers to observe cosmic evolution directly. Picture the statistical properties of galaxy distribution within the observable universe. The nearly 800,000 galaxies mapped by Webb in just a small portion of sky suggest that the total observable universe contains hundreds of billions of galaxies, each containing billions of stars and potentially trillions of planets. These numbers challenge human comprehension while providing concrete measurements of cosmic scale and complexity. The horizon problem in cosmology reveals deep mysteries about cosmic structure that Webb's observations help address. Regions of the universe that are now far beyond each other as horizons show remarkably similar properties in temperature, density, and large-scale structure. The most popular explanation for this is inflation. A tiny fraction of a second after the Big Bang, quantum fluctuations caused the universe to expand at an extreme rate, creating correlations across regions that are now causally disconnected. Consider the implications of cosmic boundaries for our understanding of universal structure. We're pretty sure that the universe is even bigger than what we can see, and here's where things get really weird. We don't actually know if the universe is finite or infinite in extent. The observable universe might represent just a tiny fraction of a much larger, possibly infinite cosmic structure that extends far beyond our ability to observe or influence. The curvature of space-time on cosmic scales affects the geometry of the observable universe and the interpretation of distance measurements. In a closed universe, parallel light rays would eventually converge, while in an open universe, they would diverge. Current observations suggest that the universe is very close to geometrically flat, but small deviations from flatness would have profound implications for the total size and ultimate fate of cosmic structure. Picture the technological limits that constrain our ability to probe cosmic boundaries. Even with Webb's unprecedented sensitivity, fundamental physical limits, the finite speed of light, the cosmic expansion rate, and the discrete nature of photons create ultimate boundaries to astronomical observation. Future telescopes may push these boundaries further, but they cannot eliminate the fundamental horizon that separates the observable universe from the larger cosmic structure beyond. The anthropic principle takes on new meaning when considered in the context of cosmic boundaries. The observable universe appears to be large enough to contain the complexity necessary for life and intelligence, yet small enough that we can observe and study its structure. This remarkable coincidence raises profound questions about the relationship between cosmic scale, physical law, and the emergence of conscious observers capable of studying the universe itself. As Webb continues to probe the edges of the observable universe, it reveals that we live within a cosmic sphere of causally connected space and time that represents both our ultimate laboratory and our fundamental limitation. The boundary of observable space marks not just the edge of what we can see, but the frontier between the known and the unknowable in cosmic structure. But perhaps the most profound revelation lies not in the boundary itself, but in what Webb's observations reveal about the cosmic architecture that fills the observable universe. Visible to optical telescopes, dust-obscured star formation, the warm glow of interstellar medium, and the infrared emission from active galactic nuclei provide complementary information about how galaxies form, evolve, and interact within the cosmic web's framework. In the cosmic dance of matter and gravity that has unfolded over billions of years, imagine the intricate architecture that Webb reveals within our observable universe. A vast cosmic web where galaxies cluster along filaments of dark matter, creating structures so large that they challenge our understanding of how complexity can emerge from the smooth, nearly uniform conditions of the early universe. This cosmic scaffolding represents the largest organized structures in existence, built through gravitational processes operating across scales from individual stars to galaxy clusters spanning hundreds of millions of light years. Picture the moment when Webb's deep field observations revealed the unexpected maturity of early galaxies. NASA's Webb sees galaxy, mysteriously clearing fog of early universe, showing that massive, well-formed galaxies existed much earlier than theoretical models predicted. These ancient galaxies appear fully developed just a few 100 million years after the Big Bang, suggesting that galaxy formation occurred more rapidly and efficiently than astronomers previously believed possible. Consider the hierarchical structure of cosmic architecture that emerges from Webb's comprehensive surveys. Galaxies don't exist in isolation, but cluster together in groups, clusters, and superclusters, connected by vast filaments of dark matter and ordinary matter. The cosmic web represents the largest scale structure in the universe, with matter concentrated along filamentary networks, while vast cosmic voids contain relatively few galaxies. Drift deeper into the physics of structure formation that creates this cosmic architecture. Tiny quantum fluctuations in the early universe, amplified by cosmic inflation, provided the seeds for all later structure formation. These primordial density variations, imprinted in the cosmic microwave background radiation, grew through gravitational collapse over billions of years to create the galaxy clusters, filaments, and voids that Webb observes today. The role of dark matter in cosmic architecture becomes apparent through Webb's observations of galaxy clustering and gravitational lensing effects. Dark matter, which comprises approximately 85% of all matter in the universe, forms the invisible scaffolding along which ordinary matter accumulates to form stars and galaxies. Webb's observations of gravitational lensing, the bending of light by massive dark matter concentrations, reveal the distribution of this invisible component and its crucial role in cosmic structure formation. Picture the process of galaxy formation as revealed by Webb's observations across cosmic time. The first galaxies formed when the universe was less than 1 billion years old, in regions where dark matter had begun to collapse into gravitationally bound structures called halos. Gas falling into these dark matter halos cooled and condensed to form the first stars, which illuminated the previously dark universe and began the process of cosmic reionization. The diversity of galaxy types and morphologies reflects different paths of cosmic evolution operating within the cosmic web's architecture. Elliptical galaxies, often found at the centers of massive clusters, represent the merger products of smaller galaxies over billions of years. Spiral galaxies, like our own Milky Way, maintain ongoing star formation in their disk structures, while irregular galaxies show the effects of gravitational interactions and mergers that disrupt their original organization. Consider the feedback processes that regulate galaxy formation and cosmic architecture. The formation of massive stars and supermassive black holes within galaxies creates powerful outflows of energy and matter that can halt star formation and reshape the surrounding cosmic environment. These feedback mechanisms prevent all available gas from forming stars, creating a delicate balance between matter accretion and energetic outflows that determines the properties of mature galaxies. The timeline of cosmic reionization represents one of the most important transitions in cosmic architecture. As the first stars and galaxies formed, their ultraviolet radiation gradually ionized the neutral hydrogen gas that filled the early universe. This process cleared the cosmic fog that had made the universe opaque to light, allowing galaxies to be observed directly and enabling the complex network of cosmic structure we see today. Picture the role of supermassive black holes in shaping cosmic architecture. Webb's observations reveal that supermassive black holes existed in the centers of galaxies much earlier than expected, sometimes when the universe was less than 1 billion years old. In May 2024, the JWST detected the farthest known black hole merger occurring within the galaxy system ZS7, 740 million years after the Big Bang, suggesting rapid black hole growth through mergers even in the young universe. The chemical evolution of the universe creates another dimension of cosmic architecture visible to Webb's spectroscopic observations. The first stars contained only hydrogen and helium, but their nuclear fusion processes created heavier elements that were dispersed through supernova explosions. Webb can trace this chemical enrichment across cosmic time, showing how the periodic table of elements was gradually built up through stellar nucleosynthesis and distributed throughout cosmic structure. Consider the environmental effects that shape galaxy evolution within the cosmic web's architecture. Galaxies in dense cluster environments experience ram pressure stripping as they move through hot intracluster gas, removing their own gas supplies and halting star formation. Galaxy-galaxy interactions and mergers, more common in dense environments, can trigger starbursts and reshape galactic morphology through gravitational torques and tidal forces. The distribution of cosmic voids, vast regions with few galaxies, represents an equally important aspect of cosmic architecture. These voids, which can span hundreds of millions of light-years, contain most of the universe's volume while harboring relatively few galaxies. The properties of void galaxies, observed by Webb, provide insights into how galaxy formation proceeds in the lowest density environments in the universe. Picture the future evolution of cosmic architecture as revealed by Webb's observations of galaxy properties at different cosmic epochs. The ongoing expansion of the universe will eventually separate galaxy clusters beyond gravitational influence, while dark energy's acceleration will prevent the formation of new, large-scale structures. The cosmic web visible today represents the peak of structural complexity in the universe's evolution. The multi-wavelength perspective provided by Webb's infrared observations reveals hidden aspects of cosmic architecture in V. As Webb continues mapping cosmic architecture across increasing volumes of space and longer spans of cosmic time, it reveals the universe as a dynamic, evolving structure where matter and energy organize themselves into increasingly complex patterns. The cosmic web represents not just a static arrangement of galaxies, but a living, breathing structure that continues evolving under the combined influences of gravity, dark energy, and the feedback processes initiated by star and galaxy formation. The architecture visible to Webb tells the story of how our universe transformed from the smooth, nearly featureless conditions of the early cosmos into the rich tapestry of structure we observe today. A transformation that created the conditions necessary for the emergence of stars, planets, and ultimately the complex chemistry that enables life itself. In the mysterious depths of cosmic space where galaxies drift apart at ever-increasing speeds, imagine the invisible force that Webb's observations have confirmed as the dominant component of our universe. Dark energy comprising nearly 70% of all cosmic content, yet remaining utterly enigmatic in its fundamental nature. This cosmic enigma drives the accelerating expansion of space itself, stretching the fabric of reality and determining the ultimate fate of every galaxy, star, and planet in the observable universe. Picture the moment when astronomers first discovered that cosmic expansion was accelerating rather than slowing down as expected. Published in the Astrophysical Journal, the research builds on Rees's Nobel Prize-winning discovery that the universe's expansion is accelerating owing to a mysterious dark energy, permeating vast stretches of space between stars and galaxies. This revolutionary finding overturned decades of assumption about cosmic evolution and introduced one of the deepest mysteries in modern physics. Consider Webb's role in confirming and refining measurements of cosmic acceleration through observations of distant supernovae and galaxies. Webb Telescope's largest study of universe expansion confirms challenge to cosmic theory, providing crucial cross-checks for previous measurements while revealing puzzling inconsistencies in expansion rate measurements from different observational techniques. These precise measurements demonstrate that the universe's expansion has been accelerating for the past several billion years. Drift deeper into the physics of dark energy and its effects on cosmic structure. Unlike dark matter, which clumps together under gravitational attraction and helps form galaxies and clusters, dark energy appears to be uniformly distributed throughout space and exerts a repulsive effect that causes space itself to expand at an accelerating rate. This cosmic repulsion operates on the largest scales, affecting the motion of galaxy clusters while having negligible effects on smaller structures like solar systems or individual galaxies. The equation of state of dark energy represents one of the most important quantities in modern cosmology. Current observations suggest that dark energy behaves like a cosmological constant, Einstein's lambda, with the equation of state parameter (1), meaning its density remains constant as the universe expands. However, Webb's precise measurements are testing whether this parameter might vary with time or space, which would indicate more exotic forms of dark energy. Picture the observational techniques that allow Webb to study dark energy's effects across cosmic history. By measuring the apparent brightness and redshift of type Ia supernovae, standard candle explosions with known intrinsic luminosity, astronomers can map the expansion history of the universe and detect the epoch when dark energy began dominating over matter and radiation. Webb's infrared sensitivity allows these measurements to extend to greater distances and earlier cosmic times than previous telescopes. The Hubble tension represents one of the most significant challenges in modern cosmology that Webb's observations are helping to address. James Webb Telescope confirms there is something seriously wrong with our understanding of the universe, as measurements of the current expansion rate disagree significantly, depending on whether they're based on observations of the nearby universe or predictions from the cosmic microwave background. This discrepancy suggests either systematic errors in measurements or new physics beyond the standard cosmological model. Consider the relationship between dark energy and the geometry of space-time on cosmic scales. The accelerating expansion driven by dark energy affects the curvature of space and the relationship between distance and redshift for distant objects. Webb's observations of high redshift galaxies provide crucial tests of cosmic geometry and help distinguish between different theoretical models of dark energy and modified gravity. The future evolution of cosmic acceleration has profound implications for the ultimate fate of the universe. If dark energy continues to dominate and its density remains constant, the universe will continue expanding exponentially, eventually separating galaxy clusters beyond the reach of gravitational interaction. This scenario, known as the Big Rip, would ultimately tear apart all bound structures in the universe, from galaxy clusters down to atoms themselves. Picture the theoretical attempts to understand dark energy's fundamental nature. The cosmological constant represents the simplest explanation, a constant energy density inherent in space itself that emerges from quantum field theory. However, quantum calculations predict a cosmological constant that is 10 to the 120 times larger than observed, creating what physicists call the worst prediction in the history of science. This enormous discrepancy suggests that our understanding of vacuum energy and spacetime is fundamentally incomplete. Alternative theories propose that dark energy might be a dynamic field, similar to the inflaton field that drove cosmic inflation in the early universe. These quintessence models predict that dark energy density could vary with time and space, potentially leaving observable signatures in the cosmic expansion history that Webb's precision measurements could detect. Other theories propose modifications to general relativity itself that could explain cosmic acceleration without requiring exotic matter. The relationship between dark energy and quantum mechanics remains one of the deepest puzzles in theoretical physics. Vacuum fluctuations in quantum fields should contribute to the energy density of space, but the magnitude of this contribution appears to be either zero or vastly smaller than quantum field theory predicts. Understanding this discrepancy may require new insights into the relationship between quantum mechanics, general relativity, and the fundamental structure of spacetime. Consider the implications of dark energy for the anthropic principle and the possibility of life in the universe. If dark energy were much stronger, cosmic acceleration would have prevented the formation of galaxies and stars. If it were much weaker, the universe might have recollapsed before life could evolve. The observed strength of dark energy appears to be within the narrow range that allows complex structure formation and the eventual emergence of life. Webb's measurements of dark energy effects across cosmic time provide crucial data for testing theories of quantum gravity and fundamental physics. The expansion history of the universe encodes information about the behavior of matter and energy under extreme conditions that cannot be replicated in terrestrial laboratories. These observations serve as natural experiments in fundamental physics, probing the relationship between gravity, quantum mechanics, and the structure of spacetime. The dark energy survey campaigns enabled by Webb's capabilities will map cosmic acceleration with unprecedented precision across larger volumes of space and longer spans of cosmic time. These observations will help determine whether dark energy represents a true cosmological constant or a more complex phenomenon that varies with cosmic evolution. The results will profoundly influence our understanding of fundamental physics and the ultimate fate of the universe. As Webb continues to probe the effects of dark energy through precise measurements of cosmic expansion, it addresses one of the most profound questions in science. What is the fundamental nature of the force that dominates our universe and determines its ultimate destiny? The answer will reshape our understanding of reality itself and humanity's place within the cosmic story. In the gentle flow of cosmic time, stretching across nearly 14 billion years of universal evolution, imagine the extraordinary journey that Webb's observations reveal. From the first flickering stars in primordial darkness to the rich cosmic ecosystem that surrounds us today. A story written in the light of distant galaxies and preserved in the deep archive of space itself. This cosmic chronicle places humanity at a remarkable moment in universal history, when the universe has evolved sufficient complexity to produce observers capable of studying its own origins and ultimate destiny. Picture the cosmic timeline that Webb unveils through its observations across different distances and epochs. The universe began in a hot, dense state, approximately 13.8 billion years ago, cooling and expanding until the first atoms could form during the epoch of recombination, roughly 380,000 years after the Big Bang. Webb's observations reveal nearly 800,000 galaxies spanning almost all of cosmic time, creating a natural time machine that allows astronomers to observe cosmic evolution directly. Consider the cosmic dark ages that preceded the formation of the first stars and galaxies. During this epoch, the universe contained only hydrogen and helium atoms floating in the darkness, with no sources of light except the fading afterglow of the Big Bang itself. Webb's infrared sensitivity allows it to observe the end of this period, when the first massive stars began to shine and illuminate the cosmos approximately 180 million years after the Big Bang. Drift deeper into the epoch of rayonization, when the first stars and galaxies fundamentally transformed the cosmic environment. These early stellar furnaces produced intense ultraviolet radiation that gradually ionized the neutral hydrogen gas filling the universe, creating the transparent cosmic medium we observe today. Webb's observations show this process occurred earlier and more rapidly than theoretical models predicted, suggesting the first galaxies formed with remarkable efficiency. The chemical enrichment of the universe represents one of the most important aspects of cosmic evolution visible to Webb: spectroscopic observations. The first stars contained only the lightest elements produced during Big Bang nucleosynthesis: hydrogen, helium, and traces of lithium. Through nuclear fusion, these massive stars created heavier elements including carbon, oxygen, silicon, and iron, dispersing them throughout space when they exploded as supernovae. Picture the gradual buildup of cosmic complexity that Webb observes across different redshifts and cosmic epochs. Each generation of stars added new elements to the cosmic inventory, enabling the formation of rocky planets, organic molecules, and ultimately the complex chemistry necessary for life. Webb can trace this chemical evolution by analyzing the spectra of galaxies at different distances, watching the universe's periodic table gradually fill in over billions of years. The formation of cosmic structure represents another crucial chapter in the evolutionary story Webb reveals. Tiny density fluctuations in the early universe grew under gravitational collapse to form the first dark matter halos, which then attracted ordinary matter to create the first stars and galaxies. Webb observes this hierarchical structure formation process, showing how small galaxies merge to form larger ones and how galactic clusters assembled over cosmic time. Consider the role of supermassive black holes in cosmic evolution, as revealed by Webb's observations of active galactic nuclei at high redshifts. These enigmatic objects, containing millions to billions of solar masses, existed much earlier than theoretical models predicted and played crucial roles in regulating star formation and shaping galactic properties. Webb's discovery of supermassive black holes in very young galaxies suggests they formed rapidly through unknown mechanisms in the early universe. The star formation history of the universe shows a remarkable pattern visible in Webb's observations across cosmic time. Star formation rates peaked when the universe was approximately 3 to 4 billion years old, during an epoch astronomers call cosmic noon. Since then, star formation has steadily declined as galaxies consumed their gas supplies, and dark energy began accelerating cosmic expansion, reducing the efficiency of structure formation. Picture the cosmic environment during different epochs of universal history. The early universe was much denser, hotter, and more violent than today, with higher rates of galaxy mergers, more active black holes, and more intense star formation. Webb observes this cosmic evolution directly, showing how the universe has become increasingly quiet and mature over billions of years of expansion and cooling. The emergence of heavy elements and dust grains visible in Webb's infrared observations represents a crucial development for cosmic complexity. These materials, forged in stellar cores and dispersed by stellar winds and supernova explosions, provide the building blocks for rocky planets and organic chemistry. Webb can observe dust formation in real time within stellar atmospheres and trace its distribution throughout galactic environments. Consider the remarkable timing of human emergence within this cosmic evolutionary sequence. Life on Earth appeared relatively early in the planet's history, but complex multicellular organisms and intelligence emerged only recently on cosmic timescales. We exist during an epoch when the universe has produced sufficient heavy elements for terrestrial planets, while still maintaining active star formation and stable galactic environments. The future evolution of cosmic structure suggests that we may be living during a special epoch in universal history. As dark energy continues accelerating cosmic expansion, galaxy formation will become increasingly difficult. In the far future, galaxies beyond our local group will disappear beyond our cosmic horizon, and star formation will eventually cease as gas supplies become exhausted. Future observers, if they exist, would inhabit a much quieter and emptier universe. Picture the anthropic perspective on cosmic evolution that Webb's observations illuminate. The universe appears to have evolved in precisely the way necessary to produce observers capable of studying cosmic history. The formation of heavy elements, the stabilization of galactic environments, and the development of planetary systems all occurred with timing and efficiency that enabled the emergence of complexity and ultimately consciousness. The search for biosignatures and potentially habitable worlds represents Webb's contribution to understanding life's place in cosmic evolution. While Webb is not designed primarily for exoplanet studies, its unprecedented sensitivity allows detailed observations of planetary atmospheres that may reveal signs of biological activity. These observations place astrobiology within the broader context of cosmic chemical evolution. The pale blue dot perspective takes on new meaning when viewed through Webb's cosmic observations. Humanity exists on a small planet orbiting an ordinary star within a typical galaxy. Yet we represent the universe's attempt to understand itself through conscious observation and scientific inquiry. Webb serves as an extension of human consciousness, allowing us to observe cosmic evolution across scales impossible for biological senses to perceive. As Webb continues mapping cosmic evolution across space and time, It reveals that we live at a remarkable moment in universal history, late enough for the universe to have produced the complexity necessary for life and intelligence, but early enough to observe the active processes of cosmic evolution still operating throughout the observable universe. This cosmic perspective places human existence within the grandest possible context, while highlighting our unique role as conscious observers in the cosmos. But perhaps Webb's most profound revelation lies not in what it shows us about cosmic history, but in how it transforms our understanding of humanity's role within the continuing story of cosmic evolution. In the profound silence of philosophical contemplation, imagine the transformation that occurs within human consciousness when confronted with Webb's revelations about the true scale of cosmic reality, a perspective shift so fundamental that it challenges our most basic assumptions about significance, meaning, and our place within the vast architecture of existence itself. This cosmic perspective represents more than scientific knowledge. It embodies a philosophical revolution that redefines humanity's relationship with the universe, and our understanding of what it means to exist within infinite space and time. Picture the cognitive challenges that arise when attempting to comprehend the scales Webb reveals. The human mind evolved to navigate local environments measured in meters and kilometers. Yet Webb shows us structures spanning billions of light years and evolutionary processes occurring over billions of years. The largest map of the universe created with Webb data shows almost 800,000 galaxies crammed into a tiny piece of sky and spanning almost all of time, revealing scales that stretch human comprehension to its absolute limits. Consider the philosophical implications of cosmic insignificance that Webb's observations might suggest. In a universe containing hundreds of billions of galaxies, each harboring billions of stars and potentially trillions of planets, Earth appears as an almost infinitesimally small mote of dust. Yet this perspective of cosmic insignificance exists in tension with the remarkable fact that this tiny world has produced conscious beings capable of mapping cosmic architecture and contemplating universal meaning. Drift deeper into the paradox of cosmic significance revealed by Webb's observations. While we may be physically insignificant on cosmic scales, we represent something truly extraordinary. Matter organized into conscious structures capable of studying the universe's origins, evolution, and ultimate destiny. Webb serves as an extension of human consciousness, allowing biological intelligences to perceive cosmic structures and processes completely beyond the reach of natural senses. The anthropic principle takes on new dimensions when viewed through Webb's cosmic observations. The precise fine-tuning of physical constants that allows complex chemistry and stellar evolution appears even more remarkable when seen against the backdrop of cosmic scale. In a universe this vast, the conditions necessary for consciousness and scientific observation appear both incredibly rare and profoundly meaningful when they do emerge. Picture the temporal perspective that Webb's observations impose on human existence and meaning. Human civilization has existed for mere thousands of years within cosmic evolution spanning billions of years. Yet, during this brief moment, we have developed the capability to observe and understand processes operating on scales far beyond human lifespans. This remarkable achievement suggests that consciousness and intelligence represent emergent properties of cosmic evolution with significance that transcends their brief duration. The question of cosmic purpose becomes increasingly complex when considered in light of Webb's revelations about universal structure and evolution. Does the universe's evolution toward increasing complexity and the eventual emergence of conscious observers suggest inherent purpose? Or do these developments represent random fluctuations within a fundamentally meaningless cosmic process? Webb's observations provide data for this ancient philosophical debate without resolving it definitively. Consider the implications of cosmic loneliness that Webb's observations might reveal. Despite mapping nearly 800,000 galaxies and countless stellar systems, Webb has not yet detected definitive signs of other technological civilizations or biological complexity beyond Earth. This cosmic silence raises profound questions about the rarity of life, intelligence, and whether humanity might be truly alone among the vast multitudes of worlds Webb observes. The democratic nature of cosmic observation represents a philosophical achievement enabled by Webb's public mission and open data policy. Unlike previous eras when cosmic knowledge remained restricted to small groups of scholars or religious authorities, Webb's discoveries are immediately available to humanity as a whole. This democratization of cosmic perspective allows every person to contemplate their place within universal architecture. Picture the spiritual and religious dimensions of Webb's cosmic revelations. For many people, observing cosmic scale and beauty strengthens rather than diminishes spiritual feeling, suggesting that the universe's vastness and complexity point toward transcendent meaning rather than cosmic meaninglessness. Webb's images often evoke feelings of awe and wonder that connect scientific observation with spiritual experience. The ethics of cosmic perspective raises important questions about human responsibility and environmental stewardship. Webb's observations reveal Earth as the only known oasis of life and consciousness within vast reaches of apparently lifeless space. This cosmic perspective argues for unprecedented responsibility to preserve and protect the biological complexity that has emerged on our planet over billions of years of evolution. Consider the psychological effects of prolonged contemplation of cosmic scale on human well-being and mental health. While some people find cosmic perspective liberating and inspiring, others experience existential anxiety when confronting the vastness of space and time. The philosophical challenge involves integrating cosmic awareness with meaningful daily existence and human-scale purposes and relationships. The educational implications of Webb's cosmic revelations extend far beyond astronomy and physical science. Understanding cosmic scale and evolutionary history provides essential context for all human knowledge, from biology and chemistry to history and philosophy. Webb's observations argue for educational approaches that integrate cosmic perspective with traditional academic disciplines. Picture the cultural and artistic responses to Webb's cosmic revelations that are already beginning to emerge. Artists, writers, musicians, and filmmakers are incorporating cosmic perspectives into creative works that help humanity process and integrate these profound revelations about universal scale and meaning. These cultural responses serve as bridges between scientific knowledge and human emotional understanding. The philosophical tradition of cosmic thinking, from ancient astronomers to modern cosmologists, finds unprecedented empirical support in Webb's observations. Philosophers from Democritus to Carl Sagan, who argued for vast populated universes, now see their speculations confirmed by direct observation. Webb provides the observational foundation for philosophical cosmic thinking that previously relied on pure speculation. The future implications of continued cosmic observation raise questions about how expanding knowledge of universal structure and evolution will continue transforming human consciousness and culture. As Webb and future telescopes reveal ever more detailed views of cosmic architecture, humanity will face ongoing challenges of integrating this knowledge with meaningful existence at human scales. As we continue processing Webb's revelations about cosmic scale and structure, we confront fundamental questions about consciousness, meaning, and purpose that have occupied human thinking since the dawn of civilization. These questions gain new urgency and complexity when asked against the backdrop of a universe containing hundreds of billions of galaxies spanning nearly 14 billion years of evolutionary history. The cosmic perspective Webb provides represents both humanity's greatest intellectual achievement and our ongoing philosophical challenge: how to live meaningfully within a universe whose true scale and complexity exceeds our wildest imagination, while still maintaining the human connections and purposes that give daily life its meaning and value. In the gentle anticipation of cosmic discoveries yet to come, imagine the transformative revelations that await us. As Webb continues its mission over the coming decades, each observation potentially reshaping our understanding of universal architecture and our place within it. The telescope's unprecedented capabilities have already revolutionized astronomy within just a few years of operations. Yet we stand at the threshold of discoveries that may prove even more profound as Webb probes deeper into cosmic mysteries and explores phenomena at the very limits of observational possibility. Picture the ongoing surveys that will map cosmic structure with ever-increasing precision and depth. Webb's systematic observations will eventually catalog millions of galaxies across different cosmic epochs, creating the most comprehensive three-dimensional map of universal architecture ever achieved. These large-scale surveys will test our understanding of cosmic evolution, dark matter distribution, and the formation of structure on the grandest scales visible to human observation. Consider the breakthrough observations of the most distant galaxies that may lie within Webb's reach, potentially revealing cosmic conditions during the first 100 million years after the Big Bang. These observations would probe the epoch when the very first stars ignited in primordial darkness, transforming the universe from a cold, dark realm into the illuminated cosmos we observe today. Such discoveries would provide direct observational evidence of processes that have remained purely theoretical since the dawn of modern cosmology. Drift deeper into Webb's potential for detecting atmospheric compositions of potentially habitable exoplanets orbiting nearby stars. While not designed primarily as an exoplanet mission, Webb's extraordinary sensitivity allows detailed spectroscopic analysis of planetary atmospheres during stellar transits. The detection of water vapor, oxygen, or other biosignatures in exoplanet atmospheres would represent one of the most significant discoveries in human history, providing the first evidence for life beyond our solar system. The systematic study of supermassive black holes in the early universe promises to reveal the mysterious origins of these cosmic giants. Webb's observations have already shown that supermassive black holes existed much earlier than theoretical models predicted, suggesting rapid formation mechanisms that challenge our understanding of cosmic evolution. Future observations may reveal the processes responsible for creating these massive objects within the first billion years after the Big Bang. Picture the detailed chemical archaeology that Webb will perform on ancient stellar populations, tracing the buildup of heavy elements across cosmic time. By analyzing the spectra of the most distant galaxies, Webb can observe the universe when only hydrogen and helium existed, gradually documenting how successive generations of stars created the full periodic table of elements necessary for rocky planets and organic chemistry. The search for the first galaxies to form in the universe represents one of Webb's most ambitious scientific objectives. These primordial galaxies, composed entirely of first-generation stars, would appear fundamentally different from modern galaxies due to their lack of heavy elements and dust. Discovering and studying these cosmic fossils would provide direct observational evidence of conditions during the universe's infancy. Consider Webb's role in testing and potentially revolutionizing theories of cosmic inflation and the early universe. Precise measurements of cosmic structure and the distribution of matter on large scales provide crucial tests of inflationary models and alternative theories of cosmic origins. These observations may reveal signatures of pre-inflationary physics or evidence for more complex cosmic birth scenarios. The continued refinement of cosmic expansion measurements promises to address the Hubble tension, the puzzling disagreement between different methods of measuring the universe's current expansion rate. Webb's largest study of universe expansion continues to confirm this challenge to cosmic theory, suggesting that either systematic errors in measurements or new physics beyond the standard cosmological model may be responsible for this discrepancy. Picture the revolutionary potential of gravitational wave astronomy working in conjunction with Webb's electromagnetic observations. The combination of gravitational wave detections of massive black hole mergers with Webb's optical and infrared observations of the same events would provide unprecedented insights into cosmic evolution, black hole physics, and the fundamental nature of space-time itself. The study of cosmic web architecture on increasingly large scales may reveal unexpected structures or patterns that challenge current understanding of cosmic evolution. Webb's observations of galaxy clustering and large-scale structure could potentially detect signatures of cosmic inflation, extra dimensions, or other exotic physics operating on the largest scales in nature. Consider the technological developments that will enhance Webb's capabilities and extend its operational lifetime. Advances in data processing, artificial intelligence for astronomical analysis, and potential mission extensions could significantly expand Webb's scientific productivity. These technological improvements may reveal cosmic phenomena currently beyond even Webb's extraordinary capabilities. The coordination between Webb and future ground-based telescopes promises to create an integrated observational network with unprecedented power. The combination of Webb's infrared sensitivity with the visible light capabilities of next-generation ground-based telescopes will provide comprehensive multi-wavelength views of cosmic phenomena across all accessible regions of the electromagnetic spectrum. Picture the potential for discovering entirely new classes of cosmic objects or phenomena that current theories do not predict. History shows that revolutionary telescopes often reveal completely unexpected cosmic phenomena, from quasars and pulsars to dark energy itself. Webb's unprecedented sensitivity and resolution may detect cosmic objects or processes that will require new theoretical frameworks to understand. The philosophical and cultural implications of Webb's future discoveries may prove as significant as the scientific revelations themselves. Each major discovery transforms humanity's understanding of our cosmic context and challenges existing frameworks for meaning, purpose, and significance within universal architecture. These ongoing transformations of perspective will continue shaping human culture and consciousness for generations to come. The educational and inspirational impact of Webb's discoveries extends far beyond professional astronomy, inspiring new generations of scientists, engineers, and explorers. The telescope's public outreach and the immediate availability of its spectacular images and data democratize cosmic discovery, allowing people worldwide to participate in humanity's greatest adventure of exploration and understanding. As Webb continues its mission through the coming decades, it will undoubtedly reveal cosmic phenomena and structures that we cannot currently imagine. The telescope represents humanity's most ambitious attempt to understand our place within universal architecture, and its future discoveries will continue expanding the boundaries of knowledge and wonder for years to come. The journey of cosmic discovery that Webb enables extends far beyond any single telescope or mission. It represents humanity's ongoing quest to understand the universe that gave birth to stars, planets, and ultimately conscious observers capable of contemplating cosmic mystery and meaning. In the gentle twilight of contemplation, as we drift toward the peaceful realm of sleep, let us hold close the extraordinary revelations that Webb has unveiled about the true scale and majesty of our cosmic home. We have journeyed together through nearly 14 billion years of universal history, witnessed the birth of the first stars in primordial darkness, traced the formation of galactic architecture across impossible distances, and contemplated our own remarkable emergence within this vast cosmic story. Picture yourself floating gently through the cosmic web that Webb has revealed, drifting past the 800,000 galaxies captured in its deepest surveys. Each one an island universe containing billions of stars and countless worlds. Feel the profound peace that comes from understanding your place within this magnificent architecture, not as an insignificant accident, but as an integral part of the universe's journey toward consciousness and understanding. The James Webb Space Telescope has shown us that we live within a cosmos far larger, more complex, and more beautiful than any previous generation could have imagined. Its observations, spanning almost all of cosmic time, reveal that the universe has been preparing for this moment of conscious observation across billions of years of stellar birth, galactic evolution, and the gradual assembly of the cosmic web that connects all things across space and time. Consider the remarkable journey that led to this moment of cosmic awareness, from quantum fluctuations in the early universe through the formation of the first atoms, the ignition of primordial stars, the synthesis of heavy elements, the birth of our solar system, the emergence of life on Earth, and the evolution of consciousness capable of building instruments like Webb. Every step in this cosmic evolution has contributed to our ability to observe and understand universal architecture. Rest in the knowledge that Webb continues its silent vigil at the edge of our solar system, gathering ancient light and decoding cosmic messages that have traveled across billions of years to reach us. Each photon it collects carries within it the story of cosmic evolution, the record of stellar birth and death, and the evidence of processes operating on scales that dwarf human imagination, yet remain accessible to human understanding. The cosmic perspective that Webb provides transforms our understanding of what it means to exist within infinite space and time. We are neither the center of the universe nor insignificant accidents within cosmic vastness. Instead, we represent something far more remarkable: the universe's attempt to understand itself through conscious observation, scientific inquiry, and the deep contemplation of cosmic mystery. As you settle into restful sleep, imagine the cosmic processes continuing their ancient dance across the observable universe. Stars are being born in distant nebulae. Galaxies are slowly spiraling through their gravitational ballet, and the fabric of space-time continues expanding, carrying cosmic architecture toward futures we can barely imagine. These processes operate on timescales that make human lifespans appear as brief, flickering moments, yet they have created the conditions necessary for consciousness and wonder. The infinity that Webb reveals extends in all directions around us, backward through time toward the cosmic beginning, forward into futures filled with continuing cosmic evolution, and outward through space toward horizons we may never reach. This infinite context provides not anxiety, but peace, understanding that we participate in processes far grander than individual existence, while finding meaning through our capacity to observe, understand, and appreciate cosmic beauty. Picture the generations of future observers who will build upon Webb's discoveries, developing new technologies and new perspectives that will reveal cosmic wonders we cannot currently imagine. They will inherit the foundation of knowledge that Webb is creating, using it to probe even deeper into cosmic mystery, and perhaps to answer questions about consciousness, meaning, and purpose that we are only beginning to formulate. The universe that Webb reveals is simultaneously vast beyond comprehension and intimately connected to our daily existence. The carbon in our bodies was forged in stellar cores. The oxygen we breathe was created in supernova explosions. And the iron in our blood was synthesized in the heart of dying stars. We are literally made of star stuff, carrying within our physical being the history of cosmic evolution and the potential for continued cosmic understanding. As consciousness gently fades into the peaceful realm of dreams, carry with you the profound truth that Webb has confirmed. We live within a universe of extraordinary beauty, complexity, and meaning. The cosmic architecture surrounding us represents not cold, empty space, but a rich tapestry of matter, energy, and possibility that has culminated in the emergence of life consciousness and the remarkable ability to contemplate our place within infinite cosmic mystery. Sleep peacefully in the knowledge that you are part of the greatest story ever told, the evolution of the universe itself, from simplicity toward consciousness, from emptiness toward understanding, from cosmic beginnings toward infinite possibility. Webb's observations remind us that this story continues, and we are privileged to participate in its ongoing discovery and contemplation. Sweet dreams among the stars. If you've enjoyed this journey through cosmic discovery with the James Webb Space Telescope, please consider subscribing to our channel and turning on notifications to join us for more explorations of the universe's greatest mysteries. Your support enables us to continue creating these peaceful, scientifically grounded journeys through the cosmos, helping all of us better understand our remarkable place within the infinite architecture of existence. Thank you for joining us on this cosmic adventure, and until next time, keep looking up at the stars.